So, ladies and gentlemen, thanks for joining us for another webinar. Oh, okay, so Maximilian apparently suggests that the chat is disabled, Fred, just so you know. Maybe you can fix that. We can get some responses throughout today's conversation. So again, welcome to this webinar. We talk about confidence in reliability. Now, before we go on, I do need to emphasize that today's discussion is going to need a little bit of prior knowledge about things like PDFs and CDFs and probability distributions, etc., etc. Got it? It's got another message confirming that the chat window is not available for our students. I'm imagining Fred will have that up and running fairly soon. And Q&A is working fine, obviously. So what we're going to talk about today is confidence in reliability, with the key word being confidence. And before we actually go into talking about what confidence means, I'm going to set the scene somewhat. And let's just say that you are working in an organization which is making something. Let's just say, for example, you work in a consumer electronic manufacturing organization, and you are manufacturing an amazing new wireless modem router, which is going to take over the world with all its wonderful features and just otherworldly focus on quality. And one of the questions you might need to ask or answer, I should say, is, can I launch this product with a 2-year warranty period? And this is a typical question about reliability. The reason being is because we want to make sure that we want to, wherever possible, offer a long warranty period with our products. The longer the warranty period, the more attractive it is to our consumers and the more likely it is to be purchased. But if we have a 10-year warranty period, perhaps we'll have too many of our wireless modem routers failing for us to be profitable. So I need to balance the warranty period against the expected number of failures we anticipate during that warranty period and the consumer expectation on what a good warranty period is. So one of the key things we want to know is how many things or what fraction of our wireless modem routers do we expect to fail in our warranty period. And some of you might have heard of this thing called a probability plot. And this probability plot is one way we can help understand what the reliability of our things are. Now, a probability plot is a really cool chart. In this case, we have this chart, which on the vertical axis, you can see is a bunch of percentages. On the horizontal axis, you can't see any numbers yet, but the horizontal axis represents how long or how old our device is. And the blue dots represent, in this case, let's just say test data. So we have on the bottom left-hand corner, we have near the 2% line, we have a single blue dot, which represents perhaps a test where we had 30 or so wireless modem routers, and that was the first wireless modem router to fail. And right at the top right-hand corner, near the 95 to 99% range on the vertical axis, you can see another blue dot, the highest blue dot, and that might represent the wireless modem router that lasted the longest period of time. Now, the reason why you want to plot data on these probability plots like this is because each probability plot is based on an underlying distribution. And a probability distribution, for lack of a better term, is a model that describes or how we understand a random process is going to behave. And if we see a straight line on a probability plot like this, it means that the underlying distribution, which created this really weird scales on this probability plot, is perhaps a good model for our random process. Now, in this case, our random process is how our wireless modem router fails. Now, subjectively, you might say that these data points seem to plot a relatively straight line. Of course, it's not perfectly straight, but When we're dealing with random data, you're never going to get a perfectly straight line. You're going to have some inherent deviations from what you might call the expectation. But it's conceivable that at least some of us might look at this data and suggest, oh, it seems to be plotting out a relatively straight line. Therefore, the underlying model on which this probability plot is based might be a really good fit. And often we might be able to draw a line of best fit through our data points and go, oh, fantastic. That's going to plot out or chart how many things we expect to fail against usage. Now, when it comes to lines of best fit or best guesses or point estimates, that's all well and good. But because the process we're observing is a random process, there's always going to be some inherent uncertainty in the inferences we make. And so we might use a software package, for example, to create a plot just like this, but put this region over the top of it. And we call this a 90% confidence interval. So in this case, we might engage or use some sort of software package which does probability plotting. We put our data in and we can perhaps, if we want to draw a line of best fit, a straight lines. But also it's usually very important to create a confidence interval because we want to gauge how confident we are in the underlying data. And I'm going to come back to this theme of confidence because confidence is a measure of you. It's not a measure of the device, it's a measure of you. And you need confidence to make good decisions. You might remember that the question at the start of this conversation was, can I launch my product with a 2-year warranty period? And some of the things you need to consider are how many things you expect to fail during that 2-year warranty period. So if we are on the horizontal axis, this green line here, the very first green line represents 2 years worth of usage. And if we draw a line straight up through our confidence region, you can see that our line intersects the top and the bottom of our confidence region at 4.6 and 16.6% respectively. And that means that based on our data, we are 90% confident that somewhere between 4.6 and 16.6% of our wireless modem routers are going to fail in the first 2 years. Now, this doesn't tell you whether you can have a 2-year warranty period because now it's up to you to interpret this information against your business goals and objectives, so on and so forth, in order to make an informed decision about whether you can extend a warranty period from 1 to 2 years, for example. But now you have information, but it's not what a lot of people call perfect information. In fact, people call this dirty information or imperfect information, so on and so forth. But in practice, this is information without any sort of adjective describing it, because every single statistical analysis is going to give you some sort of information against which you need to ascribe some sort of confidence. You can never be absolutely certain the mean or the average or the standard deviation or warranty reliability like this is going to be an exact value. If you're not dealing with confidence and uncertainty in your decision-making process, then you are not making good decisions. So reliability, in this case, is a measure of your system. But you might remember what I said just previously, confidence is a measure of you. The wireless modem router already has a reliability value at 2 years. We just need to try and somehow find out what that is, or at least get an understanding of what that is. And if we look at it using the patented random hand of failure, which is, as I understand, becoming an increasingly recognizable calling card for my webinars, this hand represents that random process we call failure. It characterizes or takes into consideration or represents all the different variations and material imperfections, seasonal weather changes, how people are going to use our modem, and essentially summarizes those different factors into a random process in terms of how it affects a random variable. In this case, our random variable is our time to failure for each wireless modem router. And of course, if we observe our random process, either we do some testing or we get field data, we might get lots of data points, in this case, 30 data points just like this. And from that, we are able to generate what we call a PDF curve. Now, PDF curve, an example of a PDF curve is a bell curve, and this looks a little bit like a bell, but it's not quite. The higher the PDF curve means the more likely a random variable is going to have a value at that point. So you can see that we'd expect our random variables, our times to failure, to cluster around the region where the highest part of our bell curve appears. And in this case, what I've done is I've highlighted what we call confidence intervals from 90% all the way down to 10% around our best guess for the PDF curve. And it creates what looks like a contour plot, like one you see on maps, which illustrate or represent how high hills are. And what you should be able to see straight away is, yes, it might be a best guess that we can ascribe to the PDF curve associated with these 30 data points, but there's lots of uncertainty, and that's uncertainty is characterized by these contours, which represent different levels of confidence. Now, where did I get this curve from? It's from statistical inference using processes we're not going to go through in this webinar, but of course, there's plenty of other resources on Accendo Reliability that can help you get there. But this PDF curve contains information. It might be enough information to make a good decision. It might not. And if it's not good enough, then for us to work out if it's good enough or not, or at least have an understanding of whether it's good enough or not, we need to ask ourselves questions which relate to our decision. For example, if it's important to understand how long it's going to take before 10% of our systems fail, how confident are you in predicting when 10% of your systems will fail based on these PDF curve or this PDF curve and confidence intervals, confidence contours? And for those of you who are aware of PDF curves, that's essentially, we're looking at the region on the left-hand side of our PDF curve where 10% of the total area under the curve exists. So with this relatively spread out or dispersed contour plot of a PDF curve, it might be challenging to get a really good understanding of when we expect 10% of our systems to fail. But if we get more and more data, and each data point contains a little bit more information that statistical inference is able to pull out, you can just see how these contours collapse around our best guess of the PDF curve. And now we have a lot less uncertainty. And now if you wanted to work out how long it's going to take before we expect 10% of our systems to fail, you can do so with a lot more confidence. And again, confidence is a measure of you. It's not a measure of your system. And all confidence is essentially our ability to take information or generate information from the world around us as it relates to the decision we're trying to make. And statistical confidence starts with the likelihood. We often talk about confidence as a measure of you, obviously, but confidence can apply to people, for example. We might be confident that someone is trustworthy. We might be confident in our own abilities. From a statistical perspective, though, confidence can be rather theoretical, rather technical. But nonetheless, it is still a measure of you because you're the one who's going to conduct the statistical inference. You're the one who controls the models. You're the one who controls the techniques. And so even though you might be putting numbers into a computer and you might be controlling what the computer gives to you, because you're the one who's ultimately in charge, statistical confidence, even using techniques that you can find in many popular textbooks, it's still a measure of you. It's not a measure of the textbook. It's not a measure of the wireless modem router. It's a measure of you. And so let's look at this in a little bit more detail because everything starts with this thing called the likelihood. So let's have a look at our random hand of failure again. And you can see that in the background, we have a PDF curve shaded in gray. We've done that test we looked at earlier where we have, it looks like about 30 data points, which might represent 30 wireless modem routers being tested for a period of time until each and every single one of them fails. Now, the idea of statistical inference is, as opposed to getting a bell curve like this and using it to generate random variables, we instead get the random variables and try and guess what sort of bell curve or any other shape of curve describes a random process we're observing. That's what inference is. We start with the evidence and try and work out how that evidence, or what might be the best way of explaining that evidence. And when it comes to random variables, that best way of explaining evidence is usually going to be described by some probability distribution, which in each one of those has its own version of the bell curve. So you might look at these data points and see that perhaps they are roughly clustered around the region where our bell curve is the highest. So if you see this and you ask yourself the question, is this PDF likely to represent the random process that generated these data points? Some of us might say yes, because it looks like the data points are clustered with the highest density around the point where the PDF curve is highest. And you can see that where the PDF curve is very, very low or apparently non-existent, it doesn't appear to be too many data points. So you might subjectively say, well, that looks like a relatively good fit. Perhaps this PDF curve is likely to represent the random process, keyword being likely. But then let's look at a different PDF curve, this one over here. And even though this is not shaped like a bell curve, it is another version of a PDF curve. The bell curve is the most commonly visualized PDF curve, one might say. This one is also a perfectly valid PDF curve, which describes another completely different random process. Now, we might look at this PDF curve and you see, the data points clearly don't cluster around the region where the PDF curve is the highest. In this case, the PDF curve appears to have a very steep cliff at the left-hand side, but that's where this PDF curve suggests the data points are most likely to occur. So if we look at these data points and this PDF curve, you should reasonably conclude that this PDF curve is less likely to represent the random process that generated these data points than the PDF curve we looked at previously. It's not impossible because failure is a random process. So each one of these data points can possibly be generated by this PDF curve in a way that creates these observed data points on the horizontal axis, but it's less likely that this is the curve that describes a random process that generated these data points. So this curve is less likely. That's obviously a very subjective thing to say. Here is our first PDF curve, which hopefully you would agree is more likely to describe the random process. So if this is a candidate PDF that could describe our data, how can we quantify its likelihood? We know this is more likely than the other PDF curve, but how do we quantify that? Well, statistically, it's quite simple. If we get this PDF curve and we look at all these data points, all we need to do is draw a line up from each data point, and where that line hits the top of our PDF curve, we stop it. We freeze it right there. And if we multiply all the heights of these lines together, we get the statistical likelihood of this particular PDF curve. And we now have a number, which I'm going to represent on this continuum over here. So the number, which is the multiplication of all these heights of these lines for each data point, is on the right-hand side of your screen right now. It's still quite low on our little continuum, but we now have a number which defines the likelihood of this particular PDF curve. And usefully, we can compare this to the likelihood of this PDF curve over here, which hopefully you'll agree with me is not a good representation of what is going on. I'm sorry, I just noted a comment from Paul saying you're not seeing the PDF curve. Paul, can you see the gray region in the background? It looks like a ramp. Can anyone else not see it? Sorry, I'd ask, can I get a show of hands of people who can see the gray region in the background? Okay, Paul, then I'm sorry, I might suggest that unfortunately it might be coming down to how it's being displayed on your screen. Yeah, apologies for that. But when I get a show of hands that adamant, it usually means it's some sort of display error. Of course, this is webinars being recorded, so in the future you can view this on another monitor and hopefully see what we're talking about. But anyway, so let's look at this less likely PDF curve over here. And remember, the way we quantify the likelihood statistically is to look at each data point we observe and draw a line up to a potential candidate PDF curve like this one, multiply all these lines, the height of these lines together, and the corresponding likelihood is represented over here. This is very, very low. And so with this approach, we can compare any candidate PDF curve for any random process. And in fact, it appears as if this particular PDF curve here is one which is based on a distribution called the Weibull distribution, and it has the maximum likelihood of any PDF curve that we try to fit to our data. And you can see how high it is on this little scale on the right-hand side. And in this case, for those of you who have used a Weibull plotting or know about the Weibull distribution, the Weibull distribution is defined by two parameters. In this case, the shape parameter or beta is 5.0864, and the scale parameter or eta is 1.1676. So you can see straight away that we can use this concept of likelihood with computers to help us to find which PDF curve is going to do the best job of describing a random process whose data we have observed. And so this is very, very useful. This is the backbone of many statistical analyses or statistical inference, where essentially we try and fit the best model for our random, the data we observe of a random process. And once we have the model of the best fit, then we can use that model to help us answer questions. But in practice, these likelihoods are difficult to use to tell us our confidence. And what does that mean? We might have the maximum likelihood, the most likely PDF curve, but we are not by any stretch saying that that is precisely the right PDF curve for our process. We have observed 30 data points, and so even though other candidate PDF curves are less likely, doesn't mean that they are not the right one. So we can't just rely on our most likely PDF curve to make decisions, because there is a chance it's not right. It might be the most likely, but it doesn't mean it is going to be the PDF curve that describes our random process. And so what we're going to do right now is see the gold standard approach to understanding confidence. And we're going to do this by going to some other test like this one. Here's our random hand of failure. In this case, we tested a bunch of different things. Sorry, a bunch of different models of a particular wireless modem router, for example. And here we have a number of data points. And the likelihood, if we assume the Weibull distribution, can be summarized by this curve here. Well, now this is getting quite deep. Where did this curve come from? Well, you might remember that the most likely curve in our previous statistical inference had a shape parameter of about 5, a scale parameter of about 1.1. And in fact, when we assume a distribution like the Weibull distribution, which has 2 parameters, in which means that it has two different numbers you need to input to define the shape of its PDF curve. Each different parameter pairing has its own likelihood. And so we can see that in this case, the surface, this wonderfully, this very aesthetically pleasing surface, the highest point of this surface corresponds with the shape parameter of 1.629 and a scale parameter of 9.137. So this tells us that a Weibull distribution with these two parameter values is the most likely distribution to describe those 30 or so data points we've just observed during our test. But you can see that this surface clearly shows us that it might not be the final or the correct underlying model. You can see there's a lot of candidate parameter pair values which still might be correct. So this likelihood curve essentially summarizes our statistical uncertainty in what the underlying model is. You can clearly see it's starting to center around a particular pairing of values, and that's going to be close to the right pairing of values for the underlying model. But because we only have 30 or so data points, this surface still spreads out over at least some area. And so how do we turn this particular surface into confidence? Well, those of us who've done some of my previous webinars, one approach is to use what we call Markov chain Monte Carlo simulation. My aim today isn't to make your head explode or anything else like that. And this is a very simple thing or easy to understand approach once you've spent a bit of time using it. But for many of us who've never used this approach, I'm about to explain before, the term Markov chain Monte Carlo simulation might sound a little bit intimidating. Well, let's try and break this down, this intimidating factor down a little bit. And then what I'm going to do now is essentially ask my computer to draw a random sample of parameter values. Essentially, I want it to create a bunch of points where the points are more likely or more clustered around the highest point of this surface, and where the surface is very low, the lowlands of this surface, we want it to be very unlikely for a parameter value to be sampled. When we do that, we get a lot of these, each black point represents a particular pairing of these parameters we've just been looking at. And my computer, you can see, is busily going away, trying to, based on the instructions I gave it, generate a bunch of different samples at different points where the points that are, where the height of our curve, this likelihood surface is the highest, we get a higher density of these points. And you can see, looking from the top, that the computer's done a pretty good job of randomly sampling all these different parameter pairs. Now, why on earth would I ask my computer to do this? Because this is the first step in understanding the confidence or the uncertainty inherent in our statistical inference. And what I can do now is, because each one of these data points represents a different Weibull distribution, I'm able to go back to that probability plot we looked at the very start, and for each one of these data points, create a line on our probability plot looking like this. And now you can see that we have a bunch of different lines, which is perhaps some of you might be thinking it's making this probability plot a little less tidy, and yes, it is. But because computers are very, very good at doing calculations very, very quickly, I can ask my computer to do this millions upon millions of times. And when I do that, it's going to create so many lines in this probability plot that I'm able to work out the region within which 90% of these lines occur. And that is how we generate our confidence interval for our data points. And that means that I can, you might recall that at the very start of this lesson, the question we were trying to answer was, can I launch my wireless modem router with a warranty period of 2 years? Well, if we go to 2 down here and draw a line straight up, and where my line at 2 years, you can see 2 on the horizontal axis representing 2 years, where each where each one of these lines from my Markov chain Monte Carlo simulation approach crosses the 2-year mark, I get a single red dot. And each one of these red dots represents essentially a sample of failure probability estimates at 2 years. And I can do things like create a histogram, which summarizes the numbers of these red dots as they were generated from my Markov chain Monte Carlo simulation. Now, this is starting to really help us work out what the confidence or uncertainty in our analysis is, because this pink histogram on the left-hand side of our chart is now summarizing our uncertainty. You can see that based on those 30 data points, we perhaps our best guess at failure probability within a 2-year period between maybe, let's just say 8%. Our best guess is there's an 8% chance, or 8% of our wireless modem routers are going to fail in the 2-year warranty period. But you can see the histogram extends all the way up to over 20% and all the way below 2%. So this is, I know human beings like having single numbers, and sometimes we pretend there's no uncertainty in our statistical inference because we just crave having a single number. But in practice, when we're doing statistical inference, you cannot deal with single numbers. We need to deal with uncertainty because there is always some level of confidence we need to express. So I'll take this histogram and I scaled it out accordingly. And now I've plotted this histogram on its own chart, and the horizontal axis is the probability of warranty period failure. And this histogram neatly summarizes the likelihood of our wireless modem router failing within a 2-year warranty period, given the test data we have. And you can use this histogram to really create some very, very cool business charts. So for example, if we know that each time our wireless modem router fails during a warranty period, we need to replace that unit, and we know that cost of each unit is $115, and we know that for every wireless modem router that we sell which doesn't fail, there's a net profit of $10. We can use this histogram to create a chart like this, which essentially summarizes our understanding of the likely profit we're going to make per unit. And so if we replace this histogram with a curve like this, we now can look at this curve, which is actually another PDF curve, and work out that based on the data we've just looked at, there's a 40.73% probability of a loss. What this means is that there's inherent uncertainty in our understanding of warranty reliability. There's a chance that warranty reliability might be low enough that we don't make a profit at all. There's around about 60% chance that the warranty reliability is high enough to make at least some profit. And the expected profit per unit is, in this case, 32 cents. So remember that this is based on a $10 profit per unit should that unit not fail. So once we take into consideration our best guess, our expected the expectation we have in the reliability of our wireless modem router, we can use this chart to work out that we expect that even though we make $10 profit per unit which doesn't fail, once we take into consideration our understanding of warranty reliability, that drops down to 32 cents per unit, because that takes into consideration all those anticipated warranty repair actions. Now, this is unfortunately as simple as you can get it when it comes to graphical representation. As a reliability engineer, this is something you can potentially put in front of your decision maker, but then it's up to you to explain what this means. You need to help your decision maker understand what the uncertainty in the decision-making process is. A lot of decision makers don't like having any probability of loss. They don't, and these are what we call risk-averse decision makers, people who don't want to make a decision where there is any chance of anything bad happening. And so our decision maker might be looking at this going, that probability of a loss is way too high, then the expected profit is way too low. We can't launch this product. On the flip side, you can look at this product and say, well, there's a 60% chance of us making a profit. In fact, if you're a gambling person, deciding not to launch this product at all means we would expect to lose money based on that decision. We would expect to make money if we launch this product, but of course it's not as simple as that. But nonetheless, we now have given our decision maker information, and if our decision maker is well versed in risk-based decision making, they should be able to look at this and understand what they have to do. If they're not well versed in risk-based decision making, then the onus is on you to talk them through what this means, especially when this is the first time a decision maker has ever been told there's a risk of something bad happening when they make a call. So that is how you can summarize confidence, at least visually, because this is a measure of us, not a measure of the system, it's a measure of us. And we're not going to go through how you get these figures in this webinar, but if you want to reach out to extend the conversation after this webinar, feel free to reach out. You have my contact details. Now, because this approach that we just looked at is complicated, lots of engineers approximate their confidence. So what do I mean by that? Well, let's go back to that single example we looked at, where I used Markov chain Monte Carlo simulation to create this confidence interval of where our true model might be for these 30 or so data points. And you might recall this is a 90% confidence interval where, based on that information, using the gold standard approach to creating this confidence region, we should reasonably expect the true model to be within this region 90% of the time. Again, this is the gold standard, but that Markov chain Monte Carlo simulation thing, even though it's actually conceptually quite simple, can be challenging to embed into software. In fact, you should rarely do that, because it's hard to guarantee that your computer, without any human guidance, is going to get this right. Typically these days, you still need to have that human oversight to make sure it gets the right sampling and to get those black points clustered around the highest point of that likelihood service. And so a lot of software packages out there which do this, or say they can do this, use a lot of approximations like this one here. So you can see this red region here is what a very popular probability plotting software package will give you when it comes to 90% confidence intervals for this particular data set. And you can see that there is a clear difference. It's not huge. It seems to be relatively accurate, or they seem to marry up pretty relatively well. But there is a clear difference between the gold standard approach to confidence intervals and the approximation you get from off-the-shelf software. But that gets worse when we have a smaller number of data points, because a small number of data points contain less information, which means it's a lot more challenging to characterize the confidence we have in analyzing the information contained in this very small data set. So if we use a gold standard approach, this is what the confidence interval looks like, the 90% confidence interval. You can see that the confidence interval is now more spread out. And that means our confidence has gone down. We are less confident about understanding precisely where the true model of our random process might be, and our statistical inference is reflecting that decrease in confidence accordingly. But that same probability plotting software I told you about, it will create confidence intervals which look like this. And this simply cannot happen. They're using so many approximations and shortcuts and so on and so forth that when we have small data sets like this, we have these weird characteristics here which suggest that the regions of our confidence interval are actually essentially decreasing over time. What does that mean? It's in a way suggesting that the older our thing gets, the less likely it is to have failed, which is simply not possible. It's statistically not possible for these confidence intervals to, confidence bounds to exist, as illustrated here. And if we look at what it means for our decision maker who's trying to work out what, for example, what our 2-year warranty period should be, you can see that when we only have 4 data points, the range between our upper confidence bound, which is in a way the one that matters the most, between the two different techniques is quite considerable. So in this case, if we use the gold standard approach to create characterizing our confidence, you can see that the upper confidence bound is approximately 5% at about 1.5 years when we use the correct gold standard approach. When we use the approximations, that goes to over 90%. So that's a huge difference in the way we characterize our confidence when we use approximations, which are embedded in many statistical software packages. Now, in the accompanying guidebook, there are some basic equations for you to use to characterize confidence for really simple scenarios. So I know Fred's favorite metric is a mean time between failure or mean time to failure. And there are many cases where we are required to use we're required to find these particular metrics based on experimental data. Now, in the guidebook, there are the equations we're about to very quickly touch on. If you need to somehow characterize the confidence you have in the mean time to failure or the mean of any process, so let's assume that we have the data that we looked at previously in this lesson. And you can see here that the data points are clustered around a central region. We've already looked at how it's more likely for a PDF curve, which has some sort of hill or bell shape to describe this random process. Now, the problem with most approaches to creating upper and lower confidence bounds on things like the mean is that it essentially starts with assuming that our random process is described with this particular weird looking PDF curve, which you can see on the gray superimposed over our data set. This weird ramp looking PDF curve is described by this thing called the exponential distribution. And I'm not going to go into what makes it special, but it's essentially the simplest distribution there is. It only has a single parameter, which is why it's used and chronically overused in many textbooks. But nonetheless, many textbooks will, when you're trying to characterize the confidence you have on the mean of any process, they usually start by assuming the exponential distribution, which is, in this case, not a good distribution to use. And the likelihood, as opposed to a slope, looks a little bit like this because the exponential distribution mean is a single value. And you can see that in this case, the red cross represents the true value, and this orange curve here represents our confidence. So this region here represents a region where we're 90% confident that the true exponential distribution mean lies. And in the guidebook, you'll have these equations here, along with the Microsoft Excel formula, which will help you use this weird thing called the chi-squared random variable. T is the duration or total aggregate size of your data points. R represents the degrees of freedom, the total. 2R plus 2 is degrees of freedom, and R is the total number of failures, and lots of other statistical gobbledygook, which we can't go into today. And CL represents the confidence level. So you want to be 90% confident, then CL is replaced with 0.9. And if you use this equation here, or this formula here, you can essentially create upper and lower confidence bounds on the mean, assuming the exponential distribution. Not going to go into it in great detail. That's how you do it. But we can see that the exponential distribution is not a good fit. And so if we were to look at our random data again, and we can see from our random hand of failure that these data points, they are clearly not described by an exponential distribution. But even though we know this is what the best guess of our exponential distribution curve looks like based on these data points. It is statistically possible for this clearly improper distribution to describe these data points. And as we generate more and more data points, the uncertainty decreases, our confidence increases, and you can see that even though it's clearly not the right distribution, our apparent confidence that this distribution is the correct one is going through the roof because those contours are getting very, very narrow. The reason why is because when we assume a model, that represents a lot of information. And when we assume, when we inject that information to a statistical inference, we get things like this every now and then. This is what being confident in fake news looks like. So it's very important before we generate confidence or try and calculate upper and lower confidence bounds that we start by using our brains. So if you are faced with a random data which looks like this, we know that it's not modeled by an exponential distribution. Let's use some of you might have heard of the normal distribution, which has a bell curve PDF. And we can see that bell curve superimposed in our data points right now. And straight away, you can see this is way more likely than our exponential distribution. You can see that the height of the bell curve seems to best marry up with the region of highest data points. So if we compare the likelihood for the exponential distribution mean with the likelihood of a normal distribution mean, we can see that by simply using a statistical inference approach, we get the right model, the confidence we have in the output of our analysis is much better. This orange line represents our uncertainty. The red cross represents the true value. And you can see that we are now a lot more confident in understanding our true value of the mean just by getting the model correct. So if you assume the exponential distribution, then you're always going to have a lot less confidence because you're always going to have a lot less confidence if the exponential distribution does not describe your process very well. So the first thing we should always do when we're trying to characterize confidence is try to understand the process. And in the guidebook, there are these equations which will help you calculate your upper and lower confidence bound using this other random variable called students t. The X bar here represents the mean of your sample, which is the mean of the data points you observed, and S is the standard deviation of those data points. R is the number of failures of the total number of data points. There's our confidence level, et cetera, et cetera. And the formula for it in Excel is also shown. All this is explained in the guidebook. But the point is that what I'm trying to make is that when you're trying to characterize your confidence, you can automatically insert a lot of uncertainty by simply not looking at the random process with your brain. So the idea of confidence is that it represents what you believe. Reliability is a measure of your system, and confidence is a measure of you. Some organizations are confident because they take reliability seriously, and the rest try and test their way to confidence. What does this mean? Well, there are organizations out there who don't measure reliability. They're confident that their products are going to be reliable because they invest a lot of time into things like Vermeers and fault tree analyses and HALT, so on and so forth, where they understand the vital few weak points of their design at each iteration and design those weak points out of their system. So by the end of that design process, they know that their device is going to be they're very confident, I should say, that their device is going to be reliable because they've spent all this time viciously hunting failures during the design process. Today's conversation has all been about statistical confidence, which, in my opinion, is a lot less useful most of the time. While it is very important in some cases to be able to create confidence bounds on warranty reliability and things like that, many organizations simply focus on good processes and good procedures and good cultures in the design and manufacturing teams to make sure that their device is very, very robust. They have this wonderful confidence, which is innately drawn from the fact they know what they're doing. They have invested a lot of time into training their people how to use FMEAs. They've invested their time into having good fault tree analyses and facilitators. They have wonderful halt technicians or whatever it is they need to do to bake reliability into their system. Organizations who don't have this confidence almost exclusively rely on testing because that's all they have, all they know. And because confidence is a measure of you, not a measure of your system, confidence can come through a number of different media, so to speak. Confidence through doing it right the first time, or confidence from data points on a Weibull plot. But if you do, even those organizations which are very confident in their devices because they have baked reliability into their system, they bake quality into their manufacturing processes, a lot of them will still do at least some rudimentary statistical testing. But even if you get to that stage and you use the wrong model, then you're going to introduce uncertainties and otherwise erode confidence, which you potentially have worked very hard to put into your system. So when you are looking at confidence in reliability, just understand that it starts with your engineering and manufacturing expertise. If you do things right the first time and you know you've done things right, if you know you've investigated failures, if you know you're trying to push your products beyond their breaking points to work out those vital few, if you know that you've successfully designed those out of your system, then you are inherently confident that your system is reliable. If you've done none of that, then you might need to test for potentially years to generate the same level of confidence, because confidence is a measure of you. And so once you work out what sort of confidence is the right sort of confidence for your scenario and for your stage of the design process and manufacturing process, that's when you then choose how you go about it. And if you need to use statistical methods to generate confidence, make sure you're aware of some of the concepts we looked at today. Make sure you are aware that, for example, probability plotting software will approximate your confidence in ways which can be quite bad. Make sure you are aware that one of the best ways to lose confidence is to not look at the data and use an appropriate model, because that model contains information. So while confidence is often seen as a very statistical concept, it is essentially a very subjective belief. Are you confident that this wireless modem router is going to last 2 years in the hands of your customers? And you don't have to get that confidence from testing. So I've got about a little under 10 minutes before we call it quits for today. Are there any questions about the things we've covered? I believe the chat window is now working, so feel free to ask questions in the chat window or through the Q&A session. Just don't forget that guidebook I mentioned. Fred has shared the link, which I believe will be on the webinar page anyway, to get access to that guidebook, which is a PDF document where you can download and enter notes into the appropriate text boxes. Are there any questions? There's no questions, then my confidence in you guys coming back for my next webinar is going down. Okay, so Dave asked, do we need to learn R and program MCMCs to calculate accurate CIs? Yes and no. You need to learn R or something like that in order to do what we've just done. So R, MATLAB, even Excel can do it if you're pushing Excel to its limits. I think the most important thing, though, is to be aware, first and foremost, that probability plotting software, the off-the-shelf probability plotting software is inherently inaccurate. That inaccuracy decreases once you get 20 to 30 data points. But if you're trying to make life-changing decisions off 4 data points, and that decision is vitally important, then either learn how to do it or get someone who knows how to do it, because you could be making a very, very bad call as a result. Maximilian, I would like to run through a couple of examples of performing the gold standard using MCMC on selected data sets lying around. What is the best way for me to learn it? Where should I go to walk myself through it? So the first, Maximilian, what is your preferred software package? And after you've answered that question, then the answer to the next question will be, what MCMC algorithm would you like to use? For R in particular, there's lots of really good ones out there. If you're going to use MATLAB, slice sample is pretty good. I've generated my own one because even the algorithms out there can struggle to get to every little bit of that likelihood surface. Excel, Minitab, and Weibull++ are the ones you have access to. So Excel is what you're going to struggle with. Minitab, you're going to struggle with as well. Weibull++, you can't do it in Weibull++ because Weibull++ uses those approximations we talked about. So we can perhaps, if you, R is very good. Python's not too bad either. I mean, to be honest, they're all really, really good. So it comes down to which one you're prepared to, you're most comfortable using. MATLAB's probably better, but you have to pay for it. And you're going to be looking for an algorithm like slice sampling, for example. Yeah, MATLAB's pretty decent. A lot of organizations prefer to use R because you can, when it comes to the basic stuff, do things really essentially do anything that MATLAB can do. When it comes to some of the higher end stuff, including creating those beautiful surfaces you saw in my animations today, MATLAB's the gold standard. Perhaps if you want to, we could talk about that offline. And one of my ideas for a course moving forward, is to teach people how to do this using some of the more sophisticated software packages out there. So I know that doesn't answer your question properly, but hopefully it started a conversation. So just for your awareness, just going back to an earlier part. So this surface and the animation associated with it was generated by MATLAB, and the coding for doing the sampling, MCMC sampling, was all based in MATLAB. R and Python are equally capable of doing it. It's just that MATLAB's a little bit slicker and has a whole suite of tools that can create pretty pictures like this. But we're not all of us are here to create pretty pictures or pretty videos like this. Does make it handy for webinars though. Any more questions? Yes, sir. The answer to your question is yes. Any more for any more? And MATLAB certainly is not free. So it's one thing to consider. As an aside, the likelihood surface for Weibull plotting or Weibull models, it tends to always have this rough triangular shape. For whatever reason, you can see that this hill isn't circular or round. It has a sort of 3 spurs heading off. In fact, when you have less and less data points, it actually turns from a triangle into a boomerang shape every single time. And that's the sort of detail that those off-the-shelf packages cannot incorporate. Essentially, one of the many assumptions they try to make is to try and fit essentially a three-dimensional bell-shaped surface over these data points. And you can clearly see that, and part of that, sorry, is to assume that it's essentially got a circular base. This clearly does not have a circular base. It's roundish, but it's got a sort of cross between a circle and a triangle. Any more questions? Thank you, Carl. So I'm becoming increasingly confident that there are no remaining questions, or at least no remaining questions. Oh, sorry. Someone asked, how do you choose the goal of the confidence of a product? That's a really good question. And the goal for the confidence, if you're talking about confidence intervals, 90%, for example, that comes down to the risk tolerance of your decision maker. So I can't tell you that as an analyst, but I can ask you or try and work with you as a decision maker to understand what your risk tolerance might be, or your risk aversion might be. So if it's a safety critical product, you might want to be 99.9% confident that an unsafe act is not going to occur. If you are dealing with sort of routine failures, where if something fails and you just simply replace it, it's no big deal, but it does add up costs, then maybe you need to have 80% confidence that you meet some sort of requirement before you move on. So there's no specific answer to that question. However, you do need to think about it from the perspective of the decision maker and their risk tolerance. What risk are they willing to accept that they're wrong? Typically in automotive, they use 50%. Does that make any sense? And the answer is hell no, because 50% means there's a 1 in 2 chance that you're right. Essentially, a 50% confidence bound. If I was to use that, then I'm going to, in a way, just be focusing on nothing much better than the best guess. Especially if you're using a one-sided confidence bound, and the 50% confidence interval or confidence bound is essentially the median, which refers to a measure of central tendency. So 50% as a rule is just crazy. You don't want to use anything below 80% as a rule. But yes, it is used in automotive industry. I know it's used, but it doesn't make any sense. Is the answer to your question. Thank you for your feedback, David, much appreciated. And Carl said, so every decision maker has a risk tolerance level. Yes, they do, even if they don't admit it. They need to have one. If they don't have one, then they don't do risk-based decision making. If there was no risk with any decision, then there'd be no need for decision makers, because we just need computers. If every decision had a zero risk option, then we just need a computer or a robot or a cyborg to simply make every single life decision for us. But life isn't like that. We can't invest money without any risk. We can't go to work without any risk. We can't play sports without any risk. Every decision we make is a risk-based decision. And so every decision maker has a risk tolerance level, whether they have worked it out or not. Hendra, thank you for your feedback. Carl, what is the range of risk tolerance? It's a very difficult question to answer, because if it's a safety critical system, there is limited tolerance for risk, as you would expect. If it's one of those failures that aren't a big deal, and the risk tolerance might be higher. So I have to push that back to you and help you ask that you work that out with your decision maker. But if it's as low as 50%, then you're essentially dealing with the best guess, and 50% is way too low. Yes, I agree with that. We don't live in a risk-free society. There is not one decision we make which is devoid of risk, including even eating a hamburger or something which is not healthy comes with some risk associated with it. That's why we have insurance companies, correct? Insurance companies are essentially that we pay them to accept our risk. So that's their service they provide. They say, we'll take the risk if you pay us money for it. Of course, that's how it's supposed to work. But insurance companies have lots of fine print in their policy to say, well, if you don't clap your hands 10 times before you jump in your car, then we don't accept risk, etc., etc., etc. But in principle, we push the risk onto their plate. There's a cost for that, and we pay them a premium for doing it. The problem with confidence, to get it higher, we need a lot of samples. In automotive, the samples are very expensive. So how can we have high confidence and make something meaningful, not rely on tests to be confident in us, like you said? Well, that confidence, like I said, that's non-statistical, comes from things like, I'll give you one example. If your company was to be serious about FMEAs and do FMEA training and get a FMEA facilitator and bake FMEAs into your design process, then I guarantee you that if that's the right tool for you, once you go through that process, once people are bought into it, once you've embedded corrective actions into your component, you will have confidence, but it has to be a cultural decision to go down that particular path. I don't know what product you're working on. Perhaps for me is, perhaps, for example, a HALT program is going to be much better or much more useful. So again, if your organization is serious about HALT, and you have a HALT testing regime, you teach people what HALT's all about, come up with wonderful corrective actions which are baked into the design of your system, then in the same way, you will generate a lot of confidence that your products are reliable. I'm just using two tools as an example. For me, is HALT. There's lots of other tools out there. The key from reliability engineering management perspective is to work out which vital few tools are going to work for you, bake those tools into your process. And if there's buy-in, if there's training, if there's facilitation, if there's all the things behind that you need to have to make those tools work, if they are all there, then you will have confidence that your product is going to work. And testing is, in organizations who are like that, and I've seen quite a few, testing is almost trivial. They don't really care about it in many cases because they know it's going to meet the requirement. They just test it in many cases just to do the final confirmation that those assumptions they made are correct. How about test sequence stress combinations instead of running a single stress that we rely on to build a reliability model? I believe you're referring to things like accelerated life testing or HALT testing, where you increase the stress. Accelerated life testing is focused on specific failure mechanisms where you're able to translate that back into real world conditions. So you're able to say that 1 week of accelerated testing is equivalent to, for example, 5 years worth of real use conditions, because it's a higher temperature or higher vibration or higher currents or higher stress. Whereas HALT is essentially going to keep increasing the stresses incrementally until you break it over and over again to find out the weak points. Either way, those, depending on what you're trying to achieve, those sorts of activities can have a really good impact on the reliability of your device, because it gives you information about what you need to do to make it more reliable. So I can't answer that question super specifically, apart from saying generally that those tools that, when used well, can really help you get on top of your reliability problems. You're talking about running a shock, then running a temperature cycle test instead of running them separately. Okay, so I think that conversation perhaps needs to be taken offline, because you're getting very specific, and I don't know your product very well. And we can talk about that offline. Like I mentioned, you got my contact details, because there are lots of different approaches to being clever with tests to pull out as much information as possible. So if you've got more specific questions, feel free to reach out after today's conversation. Any more questions? Okay, ladies and gentlemen, thank you very much for your time. Those who are remaining, thank you for your feedback. And if you have any questions, please feel free to reach out. And don't forget, confidence is a measure of you, not a measure of your system. And you can get confidence through doing it right the first time, or from testing. But testing can be very expensive. I'll see you guys next time you turn up to one of my webinars.